The best way to learn is by exploring core principles. Over the next 2.5 years, I'll take you on a systematic journey to break down the structures behind everyday things. Today, we'll explore how wind turbines actually generate electricity. Could a few slow-turning giant blades really do it? Is that all it takes? Well, actually, yes, that's true. They simply capture the power of the natural wind and, through a series of energy conversions, transform invisible wind into usable electricity. But these massive blades aren't made of ordinary metal. A single blade can exceed 80 meters in length, longer than a football field. To withstand millions of rotations, heavy rain, and extreme conditions like gales and lightning, engineers craft them using glass and carbon fiber, reinforced epoxy composite materials. They are lightweight enough to be driven by the wind, yet strong enough to resist wear and fatigue. However, the blades only rotate about 15 times a minute, far too slow for the generator to produce power. The rotational speed must be increased, but the heavy, bulky blades would easily snap if forced to accelerate. So what can be done? Clever engineers designed a gearbox, acting like an acceleration gear for the turbine. Through internal gear mesh, the slow 15 RPM speed is boosted 100-fold to over 1,500 RPM. This allows the generator to function normally, but the wind is never constant. Sometimes strong, sometimes weak, causing the blade speed to constantly fluctuate. This creates unstable power frequencies, while the grid demands precise frequency, where even a slight deviation can cause blackouts and damage equipment. So what should be done now? Engineers equipped the generator with a dual-fed system, functioning as an intelligent frequency stabilizer. When the speed is slow and the frequency is low, it offsets excess frequency. This way, regardless of wind strength, the generated power consistently meets standards. But if the turbine turns away from the wind, the blades won't rotate at all. People certainly can't turn it manually all day. Therefore, engineers installed wind tracking tools on the nacelle, anemometers, and wind vanes. They act like the turbine's nose and eyes, monitoring wind direction and speed 24/7. Whenever the wind shifts even a few degrees, they signal the computer inside the nacelle, which then activates the yaw system. Massive motors rotate the nacelle to keep the blades squarely facing the wind, maximizing energy capture. Next, the generator turns high-speed mechanical energy into electrical energy via electromagnetic induction. Simply put, the rotor inside spins among the stator windings, cutting magnetic flux lines and naturally generating electric current. However, this is low-voltage electricity that cannot be sent straight into homes. It must pass through the transformer at the tower base to step up the voltage to over 33,000 volts. This is essential to reduce energy loss during long-distance transmission and prevent power from being wasted. Once the blades spin, the speed picks up, the frequency stabilizes, and the voltage is boosted. The lights, AC units, and refrigerators in our homes can run on clean, eco-friendly wind power. To keep turbines running reliably year-round, regular maintenance is crucial. Just like cars need routine servicing, a wind turbine's core treasures are its lubrication systems and connection points. The gear mesh points of the gearbox and yaw system must always remain well lubricated. If the lubrication system fails, dry gear friction can cause malfunctions or even trigger a nacelle fire. The bolts connecting the blades to the hub and the fasteners at tower joints must also be regularly inspected and tightened to prevent loosening from long-term vibration. Every maintenance check must be thorough to prevent minor issues from becoming major failures. But standard turbines are only suited for areas with steady winds, in extreme environments with year-round calm or erratic wind speeds. Alternative generation methods must be used. So do you know what those methods are?